Hey everyone, welcome to 7.8 Intro. This is kind of an idea that we need to talk about before we get into the heart of 7.8. So I made a new section and called it 7.8 Intro, Relative Rates of Growth and Indeterminate Forms. What makes an expression indeterminate? We talked about this with L'Hopital's rule. Well, if I have infinity over infinity, we know that's indeterminate. But what if I did x over 1,000? Well, that's infinity, because infinity over 1,000. What if I did 1,000 over infinity? No matter what this number is, that number is going to go to infinity. You're getting closer and closer to 0. So I don't know whether it's infinity or it's 0. We don't know which it approaches. So because of that, we call it indeterminate. I don't know what infinity over infinity is. It doesn't reduce like you would think. Also, infinity to the 0. Well, 1,000 to the infinity is, or 1,000 to the 0 is 1, but infinity to the 0.1 is infinity. Infinity to the negative 0.1 is 0. All of these are different. So we say this one's indeterminate. The same thing with 0 to infinity. None of this makes, well, this one actually is really easy. This to the infinity is going to 0. This is really close to 0 to the infinity. It's going to 0. If you go to 0 here to 1,000, you're getting closer to 0. 0 to infinity is not indeterminate. It's 0. No matter how many times you multiply by 0, it's still 0. Here are the 7 indeterminate forms that you memorize for L'Hopital's rule. As always, you have to know these. 0 over 0, infinity over infinity, infinity times 0, infinity minus infinity, 1 to the infinity, 0 to the 0, and infinity to the 0. Okay, let's get into the notes that are new. Rates of function growth. Sometimes mathematicians talk about which function grows faster, and faster's in quotation marks because it's not what you think it means. In other words, as you approach infinity, which of the two functions will eventually pass the other and always be larger? That's kind of a generic way to say it, and that's not even technically correct, but it's a good way to think about it. Let's look at e to the x. E to the x grows extremely fast. That's why we say something grows exponentially. In fact, at 64 inches, if this was 1 inch, 2 inch, 3 inches, if this was 64 inches, e to the x would be all the way at the end of the universe. Likewise, natural log of x. It grows extremely slowly. If you have to go all the way to the end of the universe just to get to 64 inches tall. So of these two, it's very easy to see that e to the x grows a lot faster than natural log of x. So how do we compare these two? Well, we're going to look at what happens as you go to infinity. If f is bigger than g, and you go to infinity, you get infinity. Big over small is infinity. G is smaller than f or slower than f. Slow over fast or small over big is 0. And if you get a number that's not 0, we say they grow at the same rate. So, fast over slow is infinity. Slow over fast is 0. And same over same gives you a number that's not 0 or infinity. It's very similar to your horizontal asymptote rules. Okay, you can't think about this with common sense because 2x looks like it grows faster than x, but it doesn't. Because if you take an infinite limit of 2x over x, you get 2. And we said if you get a number that's not 0 or infinity, they grow at the same rate. So you say they grow at the same rate. Why do these two things grow at the same rate? Because they're both linear. And linear functions will all grow at the same rate as you go to infinity. Remember, growing faster does not mean has a steeper slope. Okay, which of these two grows faster, e to the x or x squared? Common sense would say e to the x because it grows really fast. But let's prove it. Let's take a limit. As x goes to infinity. And it does not matter which one you put on top. Well, that's infinity over infinity. So what do? I do L'Hopital's rule. That tells me e to the x over 2x. But that's still infinity over infinity. So I do L'Hopital's rule again. E to the x over 2. Now that is infinity. So, what does that tell me? I got infinity as an answer. That means that the faster one's on top and the slower one's on bottom. So that means that e to the x grows faster than x squared. Now what if I would have done it the other way around? If I would have put x squared on top and e to the x on bottom, I would come over here and I would get 2 over e to the x. That's 2 over infinity, which is 0. That would tell me that the slower one's on top. So it does not matter which way you do this problem. Okay? Relative rates of growth, there's a perfect example of it. It shows you that e to the x divided by x squared is going to grow forever. That means that e to the x is bigger than x squared. And that's relative rates of growth. Remember, take an infinite limit and see what happens. If you get infinity, the faster one's on top. If you get 0, the slower one's on top and the faster one's on bottom. If you get a number that's not 0 and not infinity, they grow at the same rate. Thanks, guys.